Okay. Thanks everyone for coming to the session. We're going to make a start. Thanks so much for joining for this session. I'm really excited to welcome this really excellent panel of speakers who will be thinking concretely about what the first decade of SAI might look like from a technical, from a scientific perspective. And yeah, welcome to the session. First up, we have Dan Visioni, and I'll get his slides up now. Dan is going to tell us a bit more about scales, magnitudes, tests for SAI.
Yeah, that's a random title. Okay. So, hi everyone. Thank you for being here. I was asked to start this session, and so I have a few, I guess, two main things I want to talk about, sort of to introduce and give the framing. This could be considered probably one of the most contentious sessions, right? Normally, a lot of us try to imagine things sort of idealized, far off in the future. It makes discussions a lot less uncomfortable. So having something that talks about the first decade of deployment does look like somebody is actually trying to plan a deployment. And I understand that might make a lot of people queasy. So here was my idea today, sort of have two different points. One on actual talking about this idea of scenarios and thinking through what is a scenario and what are we doing here. And the other one is more actually on the scales, and I think we'll probably find it interesting. So here's the first thing. I'll have two questions. The first one is, well, what's the line from actual modeling to the real world? Okay, and I normally try to really make the distinction between sort of an idealized experiment in model world and what we call a scenario, right? And this is the same that happens for climate change. Climate change has a lot of the same issues. IPCC scenarios are not meant to be predictive of the world. They don't even have a likelihood attached to them by the IPCC, and that's a very important point. They don't even show a particular preferability when they're built, right? But they are a way to sort of explore potential future. These comes with its pitfalls, and that's going to be the same for the SAI thing we'll talk about. And for instance, this has happened a lot for carbon dioxide removal. There's been a lot of criticism of the way the scenarios were created, the way they sort of made the urgency for CDR, they created in a way the need for CDR. That's not what everybody necessarily thinks. Some people would say, well, actually the IPCC demanded scenarios that, for instance, kept temperatures at 1.5, and in a way, in an integrated assessment model, that was the only way to do it. That could be a criticism of IAMs. Anyway, there's a lot of opinions, but the important point is scenarios are important, but scenarios also craft a specific narrative, and that is something that if we're thinking about things like the first decade of a deployment, we have to be able to acknowledge. But there are a few points that I made here that actually I saw Ted in the room, and these are mostly points that Ted taught me about. Scenarios don't necessarily have to be realistic, nor even desirable to be useful. And realism is really something that is in the eyes of the beholder. Different people might have different opinions of what realistic policy realism, even technical realism, right? If we come up with a scenario that is technologically wild, doesn't mean that somebody's not going to try to reach it, or we're not creating the need for it. So there has to be some thresholds of plausibility for a scenario. Otherwise, it's just an idealized experiment. And the other important thing is it is also useful to have multiple scenarios to discuss to avoid to compare the outcome, but also to avoid imagining that we're prescribing a specific outcome. This is all going to, I think, be good context. But also, it's really important to acknowledge that those that are crafting the scenarios don't necessarily have control of the narrative of what happens then, especially when they get to the public imaginary or in places like the IPCC. Let me give you an example with one modeling scenario, right? So this is the GeoMIP G6 sulfur experiment. It was created in 2013, 2014 for the 2015 CMIP6. And this was a long time ago, right? Now it's 12 years ago. It was never meant to be neither desirable nor even realistic. But then, and it's clear, right? The idea was to start SRM in the simulations in 2020. 2020 is long gone. The idea was to follow an SSP 585 scenario that is definitely not a desirable one. It's one with incredibly high concentration of greenhouse gases. We've updated sort of the injection strategies and so on, but people still use it for analysis. So there's a point in which you create your scenario for various reasons. This was modelers getting together. I was still in my undergrad when they created this scenario, right? But it's interesting how eventually, something you decide on, maybe in a day, in a room full of modelers and some impact analysts, eventually sort of becomes something established, and then maybe the narrative gets out of you. Now, given that, and that's sort of a way to say, don't blame too much the people who will talk about their own scenarios about that's what they want to do, but it's useful to keep that in mind. Let me twist that question to another one. What's the line from the real world to modeling? Because that's going to be important, especially when we think about the first decade of deployment. So the first thing is climate models are based on physical laws and observations sometimes, but observing something doesn't mean it's pretty hard to go from one observation or even a set of observation in a generalized law. And there are some things that we have in climate models that are not necessarily things that we can observe, like cloud entrainment, just to make an example. Yet they're important. And I think this is important and sometimes overlooked. We already do intentional manipulations of the environment to inform climate models, mostly for land model, nitrogen cycle. We do that. And if you look at the number, this is just one example from one CSM parameterization for the land model. In this case, plots were treated with a combination of elevated CO2, nitrogen deposition to understand what happens to nitrogen absorption. That is an outdoor experiment, okay? The problem, nobody ever found it content, and if you run the numbers of how much nitrogen they put, it's way more than a few kilograms. So, but people thought that it was useful to constrain the land model, and so it was done. So now let's think about SAI. We can definitely assume that if one were to do a deployment, before starting a deployment, there would be both I make this distinction specifically, there would be both tests to understand the technical side, the feasibility. Can we compress the gas, or what's the nozzle like? And scientific experiments to understand and improve, to increase the confidence in our modeling tools that are the only thing that can project for us for the future, to improve our confidence and our prediction capabilities, right? So we can assume that if ever a deployment happens, or at least if a deployment that makes in any way sense happens, that's a big if, but there would be something like this. Now the question though is, what scale is every experiment always going to be useful, or is there specific scales at which we think these are going to be useful? So I would say it's useful to think about this in terms of scale. So this is another figure from GeoMIP results, because that's where we had a lot of models. Other people have similar figures in these days. Generally, climate models start also pretty small. Nobody starts by dumping 5 teragrams of SO2 in the first year, right? But again, that's not because it's meant to be. It's not because it's meant to be realistic. The interesting thing that I want to point out here is that when we're trying to understand how much cooling do you get for a certain amount of injection, eventually, after 20 years, the models pretty much converge over a number, with really not too big bars of uncertainty. But look at the first years. Why are the models so different in the first years? One of the reasons is that microphysics actually, it gets probably even more messier when you're injecting small amounts, but also the fact that here, the way we're diagnosing radiative forcing, looking at the top of the atmosphere imbalance, is marred by the fact that there's internal variability, right? So for year 1, you can't really tell whether your 0.1 watt per square meter difference compared to the baseline is due to the fact that clouds have changed because of natural variability or ENSO, or whether this is your signal. This is, I think, it's important to have in mind. So for instance, I can make this assumption that roughly you get per each teragram of SO2 you inject, every million tons of SO2, you get 0.1 Celsius of cooling, 0.1 watt per square meter, but you can tell how complicated it is. Let's think about scales in the other side. This is one of the last eruptions, volcanic eruptions with a lot of SO2 that we could actually easily measure, ignoring Hunga Tonga. It was complicated. It was Ruang. 250,000 tons of SO2. TROPOMI is a satellite that looks at SO2, and this is what it saw. Barely a blip, actually wasn't detectable for too long, a month, roughly, right? But this is 250,000 teragrams of SO2, tons of SO2. So I think this is, again, another number to keep in mind. Think about 0.1 teragrams per 0.1 cooling, and this is 0.25. So here I made these slides about that actually tries to compare the sizes this way. So the largest sphere that actually made my PowerPoint crash multiple times is SO2 pollution. Current SO2 emissions from the ground, 100 million tons of SO2, roughly, more or less, year by year. Let's compare that to what I guessed, 1 teragram of SO2 that would sort of put you at the threshold of detectability in terms of forcing. That's 100 times less. And that is already what one could consider a full-fledged deployment. Now compare that to the Ruang eruption, sort of comparable, right? Interesting. And then let's imagine, well, if the big ball here, the 1 million, it was the first year of deployment, how much are you injecting every day to get to that 1 million? And that's the number, right? On a hypothetical day one of a deployment in which you're doing 1 teragram in 1 year, it looks like essentially so tiny I had to put 30 tiny dots. And the interesting thing is, right, that's 3,000 tons, which is roughly the potential load of a 777, around 100 tons. So roughly you need 30 dots, right? So you need 30 flights worth of material on day one to get you anywhere close to something that eventually looks like the threshold of detectability. So when you hear the numbers for the rest of the talks, I think these are useful to keep in mind. And I will also note that eventually to get to the point where you're close to detectability, well, the only comparison I could find is last year we had the GeoMe meeting in Ithaca, which is a very small town in upstate New York. And roughly the same proportion of inhabitants that Ithaca have to Cape Town is the same proportion of planes you would need compared to your first day one of deployment. So last thing, maybe a few guesses. This is completely wild. Please yell at me if you want. What are they actually, this is my educated guess in terms of, and definitely they need more research, but what are actually the scales at which some of the processes we need to understand in the climate model to make better in the climate models at which I think will make sense to do outdoor experiment. Doesn't mean that I endorse outdoor experiment, blah, blah, all of that, but this is my guess. And I tried to divide these, assuming the large-scale transport and then the climatic effect, that's actually what a deployment is for. Let's assume 3 scales. A microphysics scale, so actually trying to understand what happens to the aerosols when they form and coagulate and so on. A turbulence scale, what happens when you have turbulence on top of that, what happens to the dissipation of the plume, and then sort of what I call the synoptic scale, what happens with this sort of vaguely large transport that is roughly one where one has to start worrying about transboundary effects. So I took a guess of these, but I actually backed it up with some numbers, but happy to be proven very wrong. If we want to improve our fundamental scientific understanding of microphysics, so what happens to the aerosols when they form, I think we still need to be representative. As in, there are still things, I'm not saying that smaller experiments are not going to be useful. There's still a lot you could learn about processes, but if you're thinking about stratospheric aerosol formation with sulfate, I think that actually the scale that we would need is pretty high. And so my guess and my sort of back of envelope number is that at least we need sort of 100 kilogram of material, but probably that's very low, at least to begin, right? And you need to think about how you would detect and measure all of these. So there's a lot of complication we need to go for. But that's 0.1%. 100 kilogram is a lot more than some other experiments that have been proposed and somehow never happened, but it's still 0.1% of what a one plane of an initial deployment would look like. And this would essentially be almost undetectable unless you manage to track the plume pretty tight. So if you actually then want to understand turbulence and how mixing affect all of these, then you need to go and you need to develop ways of tracking that probably, I mean, we're starting to have, but probably we need to work a lot more on that. Then I think you need at least 10 times as more. That's still 1% of that, but I'm pretty confident that we need on the order of a ton to start doing experiments where we start to understand turbulence in the stratosphere, something for which actually we don't have too much constraint, especially in the wake of the plume. And finally, what if we want to start to understand whether our models are capturing well the transport across Europe, for instance? That's what this is, or across Africa, or for transboundary effects. Well, at that point, based on the fact that you would need to start tracking things probably with satellites or with LiDARs and so on, you would need to be very careful about that. At that point is the point where it's unavoidable to go at the tens of tons scale. That's 25% of one plane on day one. So to wrap up, first of all, again, it's important to acknowledge that discussing about deployment might make one more likely. We're not thinking, but I don't think we can hide forever behind this is purely idealized stuff. We have no opinions about these. Thinking about deployment creates something that is close to the conditions for deployment. That's, in a way, I think it's true. But these risks need to be balanced by another one, I think, which is, what are we missing if we don't ever start thinking about what a deployment looks like? And I think we need to start thinking a bit more seriously about exactly this point. I'm not the first person to propose this is the case, right? But I want to reiterate that point. And we'll have to acknowledge that between the current full model scale or lab chamber experiment or baseline observations and what a deployment is, there are a lot of intermediate scales. So for instance, since in this conference we've been talking a lot about governance, I do think that it merits a lot more to think about these intermediate scales and, for instance, put some numbers about what we mean by a small scale or a large scale test based on the sizes that we've talked about here. Thank you.
Pleased to welcome Wake Smith for the second talk.
Thank you. So I'm going to repeat a couple of slides that I presented yesterday. I see. And then step away from them. There has been a sort of well-worn idea of what deployment may look like that would assume we're deploying in the tropics and subtropics, and so the custom was 30 north, 15 north, 15 south, and 30 south, and this map demonstrates those points on 3 continents. This is roughly the north-south extent of Africa. Cairo is at roughly 30 north, Durban is at roughly 30 south, and so that north-south extent would be the sweet spot that is assumed to be where one would seek to deploy if one is seeking a deployment that would veil the entire globe in a protective veil. The importance from an aeronautical standpoint of those 30 north to 30 south points is that the stratosphere is low at the poles and high near the equator. And so if we're trying to deploy in the tropics, we've got to deploy quite high. My stars here are 15 north and 15 south, right at the tropopause. We would deploy above the tropopause, so at the top of this graph, around 20 kilometers altitude, has been the assumed deployment altitude that one would need to seek in the stratosphere, and that's difficult to do. Existing aircraft don't get us there. The 777 that Daniele made reference to wouldn't get us there. That's not an available aircraft for that tropical deployment. And so 5-6 years ago, a team of us developed a novel high-flying aircraft of the sort that would be needed to deploy in the tropics in that way. With the folks at Chicago, we're undergoing another under David's leadership, we're undergoing another design study to look at a different aviation concept that would get us to 20 kilometers. But 20 kilometers is not an impossible aviation task, but there isn't an aircraft that would get us there today. And so my focus heretofore has been essentially on this deployment concept and the high altitude equipment that would be necessary to get us there. And developing such an aircraft is a substantial undertaking time-wise, a decade or so. But I no longer think that that's the way we will deploy. I think I'm going to stop using the prior slides that I just showed, because I think that a much more likely early deployment concept, and that's what we're meant to be focusing on here, the first decade of deployment, would step away from the tropics and move either to the mid-latitudes or to the high latitudes, the subpolar regions. And there's a lot to be said about why we might seek to deploy, I'll call it at the poles, although precisely I mean in the subpolar regions. I think it's the most compelling place to start, in that if we invent some new ointment that can cool the planet, we should apply it where the burn is greatest. And polar amplification is causing the poles to heat up much more rapidly than the tropics. So if we want to put this new thing, this new salve, where the climate is changing most rapidly, that's at the poles. It's also the cheapest place to start, for reasons that I'll get to in a moment, although in looking at this slide just a moment ago, I realized I shouldn't have ordered things in that way. But it's cheapest. There's a lot less material that we would need to change the temperature in the polar regions by, say, a degree Celsius than would be required to deploy over the entire globe. So in terms of deployed mass, it would be a much smaller intervention. It's also easier because we could use existing aircraft to get there. Back to that tropopause height chart, if we're moving out towards the poles, then the deployment altitude required is much lower. If we're talking about 60 north and south, roughly Anchorage and Stockholm in the north, and the tip of Patagonia in the south. That's in fact only 54 south, but there's no land masses farther south from there that would make sense for deployment. But if we're deploying from these latitudes, then 43,000 feet, 13 kilometers, would put us 3 kilometers above the average tropopause height. So 13 kilometers at the poles, I'll call it, versus 20 kilometers in the equator. That's a big differential altitude-wise. And from the standpoint of aviation, it's a very big difference because existing wide-body aircraft, the 747, the 777, the 787, can get to an altitude of 13 kilometers. The Airbus aircraft have a slightly lower service ceiling, but they too can get close. And so if we were seeking to deploy in the polar regions, we could reuse existing aircraft. That would cut a lot of things. That would cut the cost of doing this because we don't have to develop a novel aircraft. It would cut the time required to get going because instead of a decade-ish span to develop a novel aircraft, it's a several-year, maybe 3-year program to develop the supplemental type certificate necessary to turn a passenger aircraft into a tanker, but that's a much lesser time span. It's also the case that the Sail 01 high flyer that I showed a schematic of earlier had a payload of roughly 15 tons. A 777 flying to 13 kilometers over Anchorage would have roughly 100 tons. I think I said 100,000 yesterday, and a few people scowled at me. That was an error. 100 tons, but 100 tons versus 15 tons, that means we need a lot fewer aircraft to loft the same mass. And so in a variety of ways, this would be a much more practical place to start. Whether it is an easier place to start in terms of governance is a mystery to me, and a mystery I hope to explore hereafter. But whether the world would find it more palatable to implement solar geo in relatively remote parts of the world where there's literally no one living in the south and a small proportion of humanity in the north, with clearer actors as to who one would go to in the early stages of governance. Whether all of that makes the governance Gordian knot easier to cut through or not is not clear to me, but that's a question that I think needs to be explored hereafter. And so if we were deploying in the subpolar regions, again, we've gone down this tropopause chart here, and this is why these stars are at 10 kilometers, so 3 more kilometers of height in order to get well above the tropopause and into the lower stratosphere. But this is a much more practicable target. So there's our 777 flying over the ice. as I mentioned earlier, what would be required for a 777, for a 787, for an A350 would be to tankerize that aircraft, install aerosol tanks into the aircraft, which requires some work. These tanks may control somewhat toxic material, and so we need some work on the environmental control system to ensure we're protecting the flight crew from the payload. So this isn't trivial, but it's not difficult at all, and wouldn't be. It presents no very difficult engineering challenges. We could also alternatively deploy between the two modes or nodes that I've illustrated, instead of all the way in the tropics at 15 and 15, or in the subpolar regions at 60, we could deploy, say, at 35 or 40 north and south, and that's what these stars represent, a lower altitude yet again. In this case, the wide-body airliners can't get there, but high-end biz jets by Gulfstream, Dassault, Bombardier could get there. And so David and I authored an article in the MIT Tech Review a year ago that looked at the sort of subscale deployment that one could do with a fleet of 10 or 15 biz jets at this altitude. And again, a much smaller deployment in that case, using much smaller aircraft, but aircraft that are more capable of getting us closer to the equator, if closer to the equator were the goal. There's a G650, which is the airplane we used in that article. And so I am now thinking about deployment not as a single geographical domain, but rather several domains that are possible. There is the tropical domain, which would require novel aircraft and a longer spool up. There are the mid-latitudes where modified biz jets would suit for a small-scale, sub-scale deployment, but a much shorter spool-up required to do that. And finally, we could undertake a polar deployment at much lower altitudes with modified wide bodies and, once again, a short spool-up. Finally, most importantly, John and Kelsey and I had a lovely couple of days up in safari. So here we are, and we saw a lot of animals, and it was really cool.
Next up, we have myself. For those of you who don't know me, I'm Alistair Duffy. I'm a PhD student at University College London. I also work with Reflective. I'm going to be talking today about some modelling results that pertain quite closely to the kinds of scenarios Wake just described. So I've been calling these high-latitude, low-altitude, or HILA SAI for short. The last couple of years of my PhD, we've been running a series of HILA SAI scenarios, myself in the UK client model, but I'll show some results from some other models too. Apologies, this is a bit more of a modelling slideshow, so be prepared to look at some more figures. So the motivation here, as we've kind of discussed, many of the studies that have gone on in this discipline have assumed tropical high-altitude SAI. And by high-altitude, I mean above 20 kilometers generally. In the last kind of year or two, there's been an increase of discussion of this question of, well, if you weren't going to high altitude, if you couldn't get that high, if you were limited to these kind of existing stock of aircraft, what could you achieve? What's the best that you could do? And necessarily, as Wake pointed out, if you were limited in your altitude, that also implies a higher latitude distribution because of this shape of the tropopause dipping as you go towards the polar regions. And so that raised this question for us, can you achieve substantial global or local cooling using existing aircraft? And we picked these altitudes of kind of 13 and 15 as being representative of two classes of aircraft, right? So at 13, you have these wide bodies jetliners. At 15, there are some other slightly smaller aircraft that can get there too. I think it's worth stressing as well that, if we are answering yes to this question, that's not necessarily a good thing, right? And I don't want to imply that I don't want to imply anything about whether or not that is a good thing or a bad thing. Here, really, we're just trying to explore the science. I also think it's worth stressing that I'll talk a bit about efficiency in this talk. And I think often when we say the word efficiency, we assume kind of cost efficiency is what people go to first. But efficiency is also a proxy for lots of things we care about, like air pollution, for example, or acid rain. So if you're talking about doubling the amount of aerosol per unit of cooling, it's not just that that's more difficult to achieve or more costly, it also has more side effects, and we should care about that. Cool. So this is a picture of the tropopause. This is a graph going from the South Pole to the North Pole, and it's sort of split into two by season, so it's actually the spring to summer tropopause in each hemisphere. And I'm showing you the range in a couple of models and also in some reanalysis products which kind of define an observational, something close to an observed tropopause height. And then I've drawn these boxes that show you, apologies, the transition to Google slides has slightly messed up the boxes, but at the top you have conventional SAI, and then you have Hiller SAI in these two kind of boxes here. So when I say Hiller SAI, what I really mean is something between around 13 to 15 kilometers altitude and somewhere in the ballpark of 50 to 70 degrees latitude. And those are numbers that are kind of ballparks. The 13 to 15 is coming from aircraft capabilities. The 50 to 70 is coming from essentially some guess around how high the tropopause is, and some evidence we have from our models about what seems to be effective at these altitudes. We're also implying a seasonality to this injection. We maybe haven't said it explicitly, but in general, if you're talking about high latitude injection, it only really makes sense to be thinking about spring to summer injection. If you're putting aerosols in the winter, that's not just pointless because there's no sunlight, it's actually counterproductive because you're still going to have those side effects from those aerosols. So for everything I'll show here, and generally I think one has to assume that if you are doing low altitude SAI, you're talking about injecting in the local spring to summer. And importantly, of course, that's different in the southern and northern hemisphere. So you have to think of this as being somewhat more of an oscillating forcing pattern than we're maybe used to thinking about. Okay, so the obvious question, does this work? And we need to think carefully about what we mean by work. But here are some plots that convince me that I think the short answer to this is yes in one sense. Right? So here are free climate models that have run scenarios of injecting at 13 and 15 kilometers at a 60 degrees north, local spring to early summer scenario. And what we see is that those colored lines are significantly different to the gray lines. So in a sense, you are getting significant global and Arctic cooling. Right? And we can talk about how significant that cooling is. But I think as a first order response, yes, at least in model world, doing this at low altitude is producing significant changes to the climate. And in particular, say, in the 13-kilometer case, what we see is something like a half to 3/4 of a degree of cooling for injecting something like 12 megatons of SO2 per year. Those numbers might not mean tons to you, but I guess the take-home I would suggest from that is those are plausible injection magnitudes. It's the large end of a plausible injection, and it's a meaningful change in global mean and Arctic temperature. Just to kind of delve into that a little bit more deeply, if we quantify that in terms of efficiency, so we can think about this in terms of cooling per unit of injection, or here per 10 megatons of injection, what I've done on this slide is compared to a kind of more standard scenario. So we take the ARISE simulations, and these are global high-altitude SAI. So I'm using ARISE here to sort of mean normal SAI, i.e. 20 or a bit kilometers, tropical injection scenarios. And we can compare in these models the efficiency against that ARISE efficiency. And what you see is that if we take the global mean temperature change, it's something like a half, maybe slightly less than a half. But, and there's a very big but here, the global mean temperature is not necessarily the best metric if you're doing a very polar intervention, because much of that temperature change is going to come from the high latitudes. And you can see that on these graphs, taking the top left graph for a start, you have this big band of red and orange color in the tropics. And what that's showing you is that although, yes, we could quote a global mean temperature change, if you then actually tried to dig into how much temperature change you see in different regions, you see that you've got a strong undercooling of the tropical regions, which isn't surprising. We've got a very polar distribution of aerosols here, with a very strong forcing in the polar regions. But I think it's really worth stressing that if we quote efficiency comparisons in terms of the global mean, that can be very misleading to the actual impact on the people most exposed to heat extremes, for example. If you then zoom into the Arctic change, you can see that actually, once you get to around 15-kilometer injection, for these Hiller springtime injections, you're getting close to the efficiency of the ARISE simulations. So just to put that in other words, a high latitude 60-degree injection scenario at 15 kilometers in the local spring and early summer generates something similar to the efficiency for Arctic and Antarctic cooling of a kind of more conventional SAI scenario in these models. Cool. This is getting a little bit more technical, but I wanted to dig slightly into why that happens. I think, certainly I was surprised by these results. When we started to model this, this was more effective than I'd imagined, right? And part of this is coming from the fact that essentially you have strong local feedbacks in the Arctic, And that means that per unit of AOD, per amount of sunlight you're reflecting, you're generating more global mean cooling than for a lower latitude aerosol burden. And that's what's shown in this middle graph here. So you see that although you've got kind of less aerosols, that's what graph A here is showing, some of that effect is being offset by having actually more global mean temperature metric change per unit of aerosol burden. And if you then multiply those all together, you get plot C, which shows you the relative efficiencies. And I think that's sometimes counterintuitive. We're often used to saying in this community, the sunlight is mostly at the equator, so aerosols at the equator do more. And there's some truth to that. There is more sunlight at the equator, but there are strong feedbacks in the high latitudes that mean that if you're just measuring temperature in the high latitudes, you can get a big signal in terms of the global mean change. I also just wanted to plot the forcing. I think this is, I found this a very interesting plot. Hopefully others will too. If we look at OIs, what we see is that essentially this forcing doesn't vary that much throughout the year, and it's a kind of a smooth signal. And actually, if we add, I stole this figure from a paper from Govindasamy Bala from 2003, which shows you the greenhouse gas forcing. And if you actually squint, it looks quite similar to the ORISE forcing. And what I take from that essentially is that ORISE is not a bad map for what greenhouse gases do, the opposite of the greenhouse gas forcing. If you then compare to what HILA 13 is doing here, it's a very different signal, right? This is a much more polar, much more seasonal forcing signal. And from that, the first order assumption has to be, what is that going to do to the climate, right? It's a very different shape of signal to the greenhouse gas forcing. And so I show this partly because, in my opinion, this is why there needs to be lots of research into these injection scenarios, because they are very different to the kinds of scenarios that we've mostly focused on as a community. And one can imagine that this forcing profile will have impacts for the type of climate response we see. But just as one data point to slightly undermine what I've just said, one thing that Govindasamy Bala and colleagues say in that 2003 paper is actually, although the forcing shape can be very different, that doesn't always bear out to being a climate response that looks that different. And here I've just plotted the Arctic temperature changes, warming on the top and then cooling in the blue colors on the bottom, by season, so the months along the bottom here, under our sort of conventional greenhouse gas force warming, and then under a global SAI, a rise, and a more HILA-style SAI. And the first order thing that I wanted people to take away from this is that actually the shapes look pretty similar. So, despite the fact that you're only reflecting sunlight locally in the summer months, and that's what the solid line is showing you, actually you still have this, fall and winter peaking temperature change that we know and kind of know well from Arctic amplification being driven by these local factors, local feedbacks. And so, despite the fact that all your sunlight reflection is happening in March, May, June, July, you're still getting the strongest temperature signal in November, December. And that, I don't think that would surprise climate scientists. I'm not saying that's a surprising result necessarily, but I think it's worth us remembering that actually, just because the forcing is different, that doesn't necessarily bear through to the local changes. Okay, and one last point, I might just skip through this quickly, but the other thing to remember is that actually the global response kind of is not necessarily as responsive to the shape of forcing as we might imagine, because the atmosphere moves heat around. And so as we compare more equatorial to more Arctic injection scenarios, what you see is that actually the local heat transports from the atmosphere start to oppose those differentials such that the outcome isn't necessarily as different as one might imagine. I wanted to finish with just a few opinions on why I think this could be a bad idea, right? Like, we should remember that there are the pros and cons to any scenario, and then there may well be reasons this is a really bad outcome compared to more global scenarios. And the first and most obvious reason is that this would generate tropical undercooling. It would be less efficient for cooling the people most exposed to heat extremes. A second reason that I think we can see in the analysis we already have is that you're generating a more seasonal cooling pattern. And that might not be quite as strong as one imagines, but you're still generating a disproportionately summer cooling in the Arctic, for example. And then, based on the lower efficiency, you're also getting more sulfur deposition per unit of cooling, and that's an important factor, right? Some more reasons that I put in red here that I'm less confident of, but I think bear investigation. Impacts on stratospheric ozone, potential impacts on tropospheric precipitation, particularly based on this kind of more seasonal forcing profile that's in the local summer in each hemisphere. I think there's big questions on what the climate response to that looks like. And then lastly, of course, there are social political risks. As Wake mentioned, the governance of the Arctic is complex, and I don't think it's obvious that this is an easy thing to govern, although perhaps it is. But I'll leave it there. Okay, so our final speaker, Lauren, couldn't make it in person, unfortunately, but she very kindly recorded her presentation for us, and I will play that now.
So before kicking off, I just want to give the following disclaimer that any subjective views or opinions that might be expressed or written in this presentation do not necessarily represent the views of the U.S. government. Okay, so for today's talk, I'm going to discuss our recently published Arctic-only scenario work in Environmental Research Letters. I also want to highlight I did not do this work on my own, and so I want to acknowledge the work of my co-authors who are listed here. One last thing to point out is that while I'm going to present a simulation of an SAI scenario that some might consider suboptimal, I'm not advocating for SAI or this particular deployment scenario. The purpose of this work is really to explore the way in which deployment constraints could be used to design scenarios and the subsequent Earth system response. Okay, so what do we mean by logistically constrained? So these are the logistical limitations that are going to be imposed by factors that are affecting your operations and can influence the overall success of your intervention. So this is your delivery platform and its acquisition timeline. Things like the chemical production plants, which are going to generate that deployed material, and also the ground facilities and the staffing that's needed to support that deployment. And so this infrastructure that you have to build up in order to support an SAI mission so that you can cool the poles or you can cool the globe is really going to take time to develop, as you've already heard from Wake. So that first 10 years is probably going to be the most impacted by these constraints. And because the environmental response is scenario dependent and that technology carries national and global security risks, this is really important to consider in your scenario design and simulation. So we really wanted to understand the implications that these technology limitations would have on deployment, and we focused on just the aircraft payload and delivery timelines. So this scenario, again, is Arctic only, which is considered suboptimal, but our thought was that rapid Arctic warming may encourage the initiation of an Arctic-only deployment in order to avoid some of the projected environmental change in the region, while a deployment plan for the Antarctic is developed. So for our scenario, we selected the A330 and the Sail 43K, which are published in the literature, and we assumed that within 5 years of authorization, 5 converted aircraft could be delivered at a rate of 5 per year. This is shown in the timeline in blue. And then within 10 years of authorization, a purpose-built, more efficient aircraft could be delivered at a rate of 10 per year, and that's shown in the chart in green. From the number of aircraft and these parameters that are shown in this table up on the left-hand side of the slide, we can calculate the injection magnitude. So this table is showing how often flights would be operated, the payload mass for each of the aircraft, and on the right is the fleet size. Below that, you'll find the injection magnitude for this configuration. So injection magnitudes start low in 2032, ramping to almost 1.25 teragrams by 2042, and increasing to about 7 teragrams by 2053. And I'll note that that's the maximum injection that we have imposed here, and that's achieved with a fleet of about 120 aircraft. For these high-latitude deployments, there are only so many airports that are really near 60 North that you can use to support such a mission, and for this scenario, we've assumed injection from the 3 large airports of Anchorage, St. Petersburg, and Stockholm. After the development and simulation of our scenario, the Boeing 777 was actually published as another potential platform for the SAI mission. And so this is an aircraft that can achieve much larger payload deliveries and really increase those earlier injection magnitudes. And as you can see by comparison in the bottom right-hand plot, that depending on the delivery rates during that first decade, you can really achieve a much higher injection magnitude by year 10 with this aircraft relative to the simulation that, or relative to the scenario that we simulated. So that's shown in the solid line, and then the Boeing 777 is shown in the 2 dashed lines. So we can take that injection magnitude with time and simulate it in E3SM as a forcing, and then look at the Earth system response against a couple of different emissions pathways. And we looked at both a high emissions pathway and a low emissions pathway, SSP 245 versus a modified version of SSP 585. And most of the results here will focus on SSP 245. For our simulations, we are using a modified version of E3SM v2. So moving on to the results, here I'm showing a time series of the global and high latitude temperature response. On the x-axis is time. Those thick lines are the average across the different simulations for each ensemble. Purple and green are SSP 245 with and without SAI. Blue and orange is our high emissions scenario with and without SAI. And what you can see pretty clearly from these results is that by 2070, there is both global and high latitude cooling. For the high latitudes, it is approximately 2 degrees of cooling under both emissions scenarios. However, that cooling signal does take a while to emerge. It's about 2 decades for the temperature response to diverge under SAI. If we look in a bit more detail and start thinking about that first decade, on the upper right is the annual mean temperature change from the first 10 years of this scenario between the SAI and non-SAI case. So blue is indicating it's cooling, and red is indicating where it's warming. And anywhere that has this hatching indicates that that change in surface temperature is not statistically significant. And so for the first decade, there really aren't a lot of areas where the temperature response is significant. You can see there's no large region in the Arctic where there's dramatic cooling. It's light and variable over this time period. If we jump a couple of decades to 2052 to 2061, results do show that expected northern hemisphere and high latitude cooling. So, but I do want to note that this Arctic-only injection doesn't result in significant cooling in the southern hemisphere, and that's really consistent with other Arctic-only scenarios. I also want to take a quick look at the annual precipitation changes. This is for the first decade on the left and the last decade of our scenario on the right. And again, similar story to the surface temperature changes, not a lot of significant change in the precipitation patterns in that first decade, but once you move on to towards the end of our scenario, there is kind of widespread drying or reduction in precipitation in the northern hemisphere. So looking at the summer precipitation relative to a 2020 reference period, we actually find that there are pretty significant changes between the baseline emissions case and with SAI. So on the left, SSP 245, and on the right is SAI. These are both against that reference period. And in both cases, equatorial precipitation patterns are significantly changed, though there are some spatial and magnitude differences between the two. So for SSP 245, you see increasing precipitation at high latitudes. Under SAI, there's decreasing precipitation over North America, Europe, and Western Asia relative to this reference period. Lastly, one key goal of an Arctic injection could be to recover or preserve sea ice. And so what I'm showing here are the March and September sea ice area time series for our cases. And as you can see, March sea ice loss slows, but September sea ice really does continue to decline and falls below what would be considered an ice-free Arctic under all cases. However, I really do want to highlight that there is both model and scenario dependence here. E3SM has some sea ice biases, but also our scenario design caps the injection at 6.7 teragrams, which is really likely limiting the sea ice recovery potential. Higher injection rates can effectively restore sea ice extents. And that's backed up by some previous results by Walker-Lee back in 2023. So to summarize this talk, we simulated a logistically constrained scenario for the Arctic, really focusing only on aircraft delivery timelines. And our results show that high latitude cooling does take a couple of decades to achieve, especially when the injection magnitude is slowly increased. And as a result, those early deployment temperature changes were pretty low and variable. Similarly, the early deployment precipitation changes were also low and variable, but this suggests that maybe asymmetric deployment could be temporarily maintained, and that would provide time for, say, Antarctic infrastructure to be established for that symmetric deployment. So with that, I'm going to conclude my talk. I'll leave the rest of this summary information for you all to read. I want to say sorry for not being able to join you in person, but also thanks to you and the panel for this opportunity.
And for that, I'll pass over to Dakota Greener now to chair the question session.
Hi, everyone. Thank you for being here. I'm Dakota. I lead Reflective and have the privilege of working with a lot of the folks here on the panel day to day. I'm going to mostly just moderate the Q&A, but really quickly wanted to just reiterate one point, make one quick plug, and then tee up the first question. So the first point, and this is something that I think Dan mentioned, but right as we were kicking off, want to be very clear that us putting together this panel is not endorsing deployment. But I think we feel very strongly that dodging questions of plausibility means that we can't honestly assess the impacts of SAI. So it's uncomfortable potentially, but I think it's absolutely necessary. Now on to the quick plug. I think all of the talks here have talked about sort of two different axes, this question of feasibility or plausibility and a separate axis around the impacts. And there are uncertainty on both of those dimensions. So Lauren and Wake talked a lot about some of the questions vis-a-vis aircraft engineering, the timelines, the flight ceilings, the payloads, et cetera. The second axis is around impacts, and we are just beginning to scratch the surface in terms of understanding the impacts of these potential high-latitude deployment scenarios. So the quick plug, we have an RFP on the site at the moment. We are open for people submitting proposals because we think that this urgently needs to be studied, and specifically, are there trade-offs associated with some of those questions around aircraft engineering? So are there ways that we may want to push for something that is logistically a little bit harder, but actually turns out to be much preferential in terms of outcomes? And so that brings me to the first question that I want to pose, which is one around maybe a new moral hazard, a new question that we need to consider, which is, as we talk about logistically easier but potentially less optimal scenarios, does that distract from work to develop the technology needed for better or best case deployment?
I don't see that it does. I'll keep it short. The magnitude of upfront capital investment that would be required to develop the supplemental type certificate, which is the permission to convert an aircraft and still have it be airworthy, that's in tens or maybe $100 million. The cost to develop a new aircraft of the sort we discussed here is many billions of dollars, and so it one of the elements of utilizing existing aircraft is that there's a much lower capital hurdle at the outset. Does that low capital hurdle distract from the high capital hurdle thing of the later thing? Not materially, as I would see it. The latter is a much bigger intervention.
Let's see. David, I'll go to you, then over to Andrew, then Liam.
Alistair, quick kind of question. Do you have maps of deposition? And obviously for Lauren too, but she's not here. And Wake, I think you laid out some good reasons why these polar scenarios might make sense, and I think those make sense. But I'm really curious why you're not saying the obvious counter that Alistair did mention. I really want to ask. So one of the most basic things we know about climate is that added temperatures are most harmful in hot regions, may even be beneficial in cold. And this isn't actually uncertain. This is one of the things we've known for 40 years. And so if you're going to do deployment that offhand you'd expect to not benefit the people who will be harmed the most, who are often poor people in hot countries, and maybe have a kind of reverse effect on global inequality. It feels like at least mentioning that is important, because I'm worried there's a tipping phenomena towards assuming these are kind of superior ideas that I hear around, and I think they may be. I don't think we know, but I think there's some really obvious reasons why they might be kind of questionable in kind of basic utilitarian ethics.
I can take the technical question first. Not yet, but we will do soon. And then maybe I can just also comment on the second question to say I broadly agree, but it is also worth stressing, if you're very worried about AMOC collapse or you're very worried about sea level rise, there are arguments on the other side too, right? So, yeah.
Actually, I'll steal the microphone also. Oh, first, wait, fine.
A caveat that you're right, I should add to the standard shtick. But I think there are some things that we don't yet know. One of them is whether the governance of a high-latitude deployment whether it would be easier to somehow assemble permission for that. And I don't know the answer, but that might lead one in one direction or another. As well, if the world, rightly or wrongly, was worried about risks of deployment over populated areas and agriculture, that too might favor a more remote deployment. But I'm not asserting either of those things. I'm just saying those are possible counter-arguments to the counter-argument, utterly valid counter-argument that you have raised. If this polar deployment concept were done, one should expect charges of climate colonialism right from the outset. I hear you.
Follow-up question to that. I'm using my moderator's privilege. How do we think about this as a local or a global intervention? And that's a question I'd love to pose to the speakers, but also to the audience.
I think that's a tough one, and well, I'll add one piece to that. So now there's a lot of discussion. I mean, John is here, so probably John can also say something. But I will point out one thing. While we were writing the AGU ethical guidelines for SRM research, there was originally a point about the Arctic being a global common, and oh my God, that upset some people in the Arctic. And I learned a lot because Ilona. I spent an hour on the phone with Ilona about these. So yeah, I think it's a really good question, but I think there's a lot of really heavy answers to that in terms of who does the Arctic belong to, and even worse for the Antarctic in some senses, even though nobody lives there.
Can I just go in quickly on that? Yeah. I think it's also worth stressing that we often use the word Arctic, but the latitudes might be in the 50s or low 60s, and that actually, it's a much broader community of people than the Arctic. And I guess I would answer the question that we should still think of these things as being global, right? In the sense that the aerosols would fall down on the heads of Arctic communities, certainly, but also many people living in the mid-latitudes.
And I would echo that last point. It's clear per the paper that Ali developed that the intended, the deployment points may be polar-ish, but the impacts, both direct and indirect, are pretty global. So I wouldn't argue that this is a polar-only intervention.
Andrew.
Yeah, question mainly to Dan, although other people might like to chime in. You're talking about your sort of turbulence deployment basically being around in the sort of 50 to 100 kilo scale. And that's very feasible to do within 100 days or so from today's date. So to do that kind of intervention, SO2 takes quite a long time to sort of metabolize in the atmosphere, right? H2SO4 is essentially instant, but the distribution mechanics are a lot harder. But if you were to distribute H2S or CS2, would the detectability of those compounds and the ability for you to gain meaningful results from those injections be appropriate, or are you really saying that you wouldn't learn anything unless you were doing direct aerosol injection at that scale?
Yeah, I think that's a good question in the sense that this is exactly the kind of things one would need to think through, and what exactly are you trying to observe, right? Sure, I say SO2 because that's my bias, but any sulfate compound that oxidizes, The scales of oxidation that you're thinking about, though, might be biased by large injections in the case of sort of a Ruang kind eruption, where you get a month because OH is it's photochemically limited. But for instance, this could be a thing, right? How long would it take? What do we expect are models that do not work at that scale, by the way? A grid box of a climate model is way less than the 50 to 100 kilograms. So we would need to first do many more studies sort of on box model side to understand what are the time scales of oxidation. I don't think actually at that scale the temporal changes are that much of importance. And so to me, yes, the thing would have to be you get the entire from the SO2 or whatever sulfate precursor you put to the oxidation to the beginning of the aerosol processes. And again, it depends on what you're trying to observe. One of the things I was thinking about in the case of that turbulence is if you have the wake of not him wake, but the wake of an aircraft, what happens to the sulfate the moment you drop it from the wake? Is it affected by the wake of the aircraft, or does it drop? What happens? At what temperature is the sulfate? There's tons of stuff that if you sit down and think about even what it would take to do 100 kilograms. Again, I'm not claiming I'm the only one thinking about this right at all, but what I think about is there's a lot of stuff where you actually need to figure out what's the temperature of the plume. Does it drop down by 500 meters, and so the turbulence from the wake doesn't actually affect that? The turbulence in the stratosphere at those scales, which is really not a scale at which Rossby wave breaks, so it's much less than that. So this is really internal turbulence in a way. I think there's tons of stuff to think about. So you say you could do it in 100 days. I would counteract by saying, sure, and learn essentially nothing, because the amount of work that you need to do to figure out what instrument to put, what to observe, how to do it, where it's actually a 2 years program. Even for a serious, I expect that it would take no less than 2 years, being super optimistic and having all the money in the world, to have a program that would allow you to say something meaningful about modeling or about what we care about, even for a 100 kilogram experiment, to do it seriously well.
Can I also just note I have been fascinated watching scientists talk about these different sulfur compounds without noting the safety difference that some of them imply for the flight crew, for the ground crew, and for the uninvolved public if the plane lands upside down. So there will be other considerations besides mere efficacy that will ultimately play into the choice of sulfur compounds, let alone other things.
Alistair, you briefly mentioned it in yours, but could we get the quick 101 on like poleward heat transport? Like, if you cool the Arctic, heat's going to go up, or the poles. He's going towards the poles. How much? How fast? Will bad things happen in other places in the world? Will eventually, at some level of cooling, will bad things start happening? Do I need to be worried about this? When should we start worrying about this? Like, what? How relevant is that question to what we're talking about here?
I'm not sure a quick 101 is possible, but I think it's a big open question, right? And I think that's an important question. Basically, in my opinion, the climate dynamics needs a lot of study, right? And that's kind of why I showed these forcing plots, to say that this is a very different style of forcing, and there's a big package of work to understand what that means for climate dynamics, right? I guess the first thing to say is that the Arctic is already warming faster, and so if you're undoing some of that, then yeah, one has to think carefully about how that affects heat transports, basically.
I'm just going to add that it's very easy to have the output of a climate model to tell you what poleward heat transport is. It is one of the insanely hard things to measure. And so this is another one of those things in which you can't just observe energy fluxes that easily, right? I mean, it's actually a huge challenge. You need to do it through actually radiative fluxes and then figuring out what's the ocean part and the atmosphere part. So this is another thing for which we actually, and Ali had this slide with the tropopause height. This is another one of the things. How well are our climate models reproducing poleward heat transport, not just in the climatological mean, but on a year-to-year basis, what would we need? What kind of, showed reanalysis. We know reanalysis are also not great compared to balloon sondes for tropopause height. How do you define the tropopause height? God, there's so many questions, but they're so exciting.
John and then Frank.
Yeah, just briefly on that heat transport thing, of course, one of the primary worries is AMOC, and generally speaking, that is declining a lot with faster greenhouse gas emissions. So this, you haven't checked it yet, as I understand, but it would be very good to know what happens as a response to this cooling. In terms of the kind of local versus global stuff, I think it's really important to point out that the global benefits don't ever triumph over the rights of local people, because that's a one-way trip to fascism. So we always have to respect the local rights, but I believe that it's possible to imagine win-win scenarios where you have local benefits as well as global benefits. And just to give you 3 examples what they might be, we know from participatory workshops and surveys that people in the Arctic care about what happens in the global south as well, especially to the poorer regions. Secondly, there are enormous benefits to avoiding, for example, sea level rise. And if the Arctic ice sheets were monetized in such a way as recognized as a global good, then the benefits of avoided flood damage would empower peoples of the Arctic and motivate them to do what they can to conserve the cryosphere. Yeah, I think I'll leave it there for now.
Hi, I just have 2 quick questions. One is, Daniele, when you're saying it's observable, it was not clear whether you meant the scale of something, whether you were just referring to satellites. I mean, there's huge differences how you observe it, so just a quick thought on that. And the second one is, I'm still surprised that one doesn't see more on this idea of putting compounds into the tropical pipe, like OCS, that slowly, and they'll react, as they're so slow, they'll react away from the actual equator, and you could do it very easily and without needing much other aircraft as well, and it would start at much sooner at mid-latitudes.
Yeah, so on the first one, yes. I had that in mind, and I didn't say it when I was thinking about the different scales, but definitely you would have to think of a system of observation that allows you to, for instance, both look at what happens above, in the middle, and behind and below that. For 50 to 100 kilograms, there's no way you can. This is well below the threshold of a satellite. So I was thinking of the third scale when you start to look at turbulence. And actually, I think this is one of the things I'd love to work on more. And we have an ARIA-funded project on these. At what scale for a satellite like Tropomi are you able to start detecting sort of the border of the plume, and when turbulence essentially starts dissipating the plume below detectability levels? Right? And what does that tell you, for instance, if you look at it for small volcanic eruptions, in terms of how well mixing happens in the stratosphere? Yeah, we can talk more about that. So for carbon sulfide, I would say yes. We wrote that paper a couple of years ago with Ilaria. It was an interesting thought exercise, and again, there's actually some other work by other people below in the poster session. Yeah, I feel like everybody will say, well, carbon sulfide is actually really toxic. A bit, so that's a thing that keeps people away. It's an interesting thought. Maybe the fact that it's so feasible means that people don't want to talk about it. But yeah.
Yeah, I guess coming into Ali's paper, I was expecting polar SAI to be much more polar and much less effective. I'm right to be shocked and surprised by the findings that it's half as effective and much more global.
I guess I would say it's only half as effective using the global mean temperature metric, which is, it can be misleading if you're getting a lot of that cooling in the poles. I think that's my answer. It surprised me too. But.
And also it means you haven't read any of the other papers that were published before that on Arctic deployment. Because no, it's a total agreement. Actually, the only surprising result here is Lauren Arctic sea ice in E3SM not recovering, because in every other simulation it seems to be recovering very well. So that sounds like a huge uncertainty to me. Yeah.
Apologies for my ignorance, but I just wanted to understand, why is the comparison of an SAI impact being done with the SSPs and not with the pre-industrial kind of a situation? And then you would basically compare it with the climate versus the pre-industrial and be able to contrast the impacts to show that it's actually reducing the impacts of climate, which was being talked about in the context of sea level rise, and therefore there are benefits on that side, and of course there are new introductions with regards to risks, but with a reduced level than what you would have basically experienced with an enhanced climatic condition. So it's just a thought, but I'm just thinking whether, the results could be presented in that manner would be more convincing for people to accept it.
I guess from my perspective, we're really motivated by kind of some sense of plausible near-term scenarios, right? So going into the future, following some emissions backgrounds. Certainly there's loads we can learn scientifically from comparing to pre-industrial, and there are GMIP scenarios that do that, and I think they're very valuable too.
There's some literature on these, wrote a paper last year making this exact point, that depending on the period you compare against, you can highlight different sort of, in a way you could call them benefit or risks, or positive or negative. And this is a challenge that we always face as modelers when we try to plot our stuff, right? Does this look too good, so like we're selling SAI, right? And in a way, that's a risk. Though I will say there are also some specific reasons in which, well, sure, but we don't live in the pre-industrial, and we also adapted, communities have adapted since the pre-industrial, so there's also a point in which if you're really trying to convey some message about how it will look in the future compared to now, pre-industrial is long gone and nobody remembers what it is. But yeah, I'd love to point out 2 more discussions about these. There's a lot of interesting things. It's a good point overall.
Just a final plug that I forgot to mention in my talk. We have a discussion on experiments of this kind at JMIP on Friday, so I would encourage people to come along for planning that. And I should also shout out locally and Matthew Henry, who are in the room, who have been running some of these simulations.